Question number 1. What is needed to accurately represent all physical quantities? So we know that to represent all physical quantities, we need a numerical magnitude and a unit. Now the unit doesn't have to be SI unit, it doesn't have to be a base unit, it could be a derived unit or anything. We just need a numerical magnitude and a unit. So that's C. A voltmeter connected across a resistor in a circuit reads 3.6 volts. What could be the current in the resistor and the resistance of the resistor? What could be, right? So we know that V is equal to IR. So the product of current and time should be equal to 3.6. Now we have to take so if you look at all of these, we have to take care of the prefixes over here. So the prefixes should be, uh, able to give us 3.6 exact. So if we choose, for example, 150 milliamps, okay, so so 150 divided by 1000 times by 0.24 times by 1000, we will get 36. Okay. However, let's try another way. Let's say we have 2.4 kilo ohms and 15 milliamps. We still get 36. Okay, so now let's try 1.5 and 0.24 mega ohms. And 1.5, we get 360. So that means the only thing is left is 15 and 240 at the end. So uh, 15 10 raised to power minus 6 times by 240,000. And that's what is giving us 3.6. So just a simple, plugging in the values. In an experiment to determine the acceleration of free fall g, the time taken t for a ball to fall through the distance s is measured. The percentage uncertainty in the measurement of s is 2%. The percentage uncertainty in the measurement of time is 3%. The value of g is determined using the equation shown. What is the percentage uncertainty in the calculated value of g? So if we just do the fractional or the percentage, the percentage uncertainty of g will be impacted by square of time and s. So we just have s plus 2 delta t over t times by 1%. So basically, we have s 2% plus 2 times by the percentage uncertainty of time. So 2 plus 3, 2 plus 6 is 8%. So that's 8%. Which quantity is a vector? Okay, so the first one, momentum, is a vector. Speed, temperature, Young modulus, they are all scalars. A particle accelerates from rest. The graph shows the variation of the velocity v of the particle with time t. Which graph shows the variation of velocity v with acceleration of the acceleration a of the particle? So this is very interesting. This is telling us that we have constant acceleration as the gradient is constant, as the gradient is not changing. The velocity only should be increasing, the acceleration shouldn't be increasing. So as you can see, none of these options are right, only this one. The graph shows the vertical velocity of the parachutist during the first 20 seconds of her jump. Approximately how far does she fall before opening her parachute? So how to identify where her parachute opens? It's where a sudden decrease in velocity starts. So approximately right over here. So we have, let's call that 11, 12, 13. 13, let's call that 13 seconds. Okay, so since we just need an approximation, we can take the area as a trapezium. Okay, since we just need an approximation. Okay, so approximation would be half times by 13, and this is going to be 5, 1, 2, 3, 4. No, wait, 2, 3, 4. Right. So 13 plus 4 times by 60. So 17 times by 30, 510. Yeah, so it's going to be, so this is our approximation, is going to be just slightly more than that because of the missing area that we have over here. So just slightly more than that. So that's 570. Okay. What is the definition of linear momentum? That's just the product of force and velocity. Sorry, product of mass and velocity. So that's C. A mass of 0.2 kgs is suspended from the lower end of a light spring. A second mass of 0.10 kgs suspended from the first mass by a thread. The arrangement is allowed to come into static equilibrium, and then the thread is cut. Immediately after the thread is cut, what is the upward acceleration of the 0.2 kgs mass? Okay, so when the masses are connected, the tension force in the spring is going to be equal to F is equal to the combined weight of that. So 0.2 plus 0.1 times by 9.81. Okay, so the upward force will be that. So when that finally thread is cut, this same force minus this weight of 0.20 g will be equal to the ma. Okay, so this is g over here basically. So 0.2 g plus 0.1 g minus 0.2 g equals to 0.2 a. So as you can see, 0.2 g, 0.2 g cancelled. We just have acceleration equal to 0.1 times by 9.81 divided by 0.2. So 0.1 times by 9.81 divided by 0.2, that is 4.9 meter per second squared. 9. A snowflake and a raindrop are in still air. They both fall from rest at the same time from the same height, far above the ground. The snowflake and raindrop contain the same mass of water. Assume that there is no evaporation or melting. Also assume that for a given speed, the drag force acting on the snowflake is greater than the drag force acting on the raindrop. Which statement about the snowflake and the raindrop is correct? Okay, so before we even see that, so if I have snowflake and a raindrop, the mass is the same, so that means that these are both are mg, but the drag force fs, fr, that is the difference, right? So if the drag force is more on the snowflake, that means acceleration of snowflake will be less than the acceleration of raindrop. That means less speed, more time to reach the ground. So raindrop takes more time than the snowflake to reach the terminal velocity. That is also correct because it's taking more time to reach the drag force level 2 weight. So I think that that is the only thing that's correct. Raindrop doesn't take more time. They don't reach this. They may or may not reach the same terminal velocity. Yes, that if they have the same mass, then yes. No. They will not, because obviously the drag forces are different. They take the same amount of time to reach the ground. Okay, so why? Sorry, my bad. Since by the time the raindrop achieves terminal velocity, the acceleration would have caused the velocity to decrease by so much more than the snowflakes. So that's why they take the same amount of time to reach the ground. Definitely not correct. That means only A is correct. Okay, all right. Two trolleys are held together on a horizontal surface with a compressed spring between them. When they are released, trolleys lose contact with the spring. trolley of mass 2 kg moves to the left at a final speed of 2 meters per second. Okay, so 2 meters per second. We don't know the speed of this. Okay, but we know that once they're released, the momentum will be the same. So 2 times by 2, 1 times by, if this is 4, then obviously 1 times by 4 will be equal to 4. So how much elastic potential energy was stored in the spring? So total kinetic energy is actually coming from the total potential. So total kinetic energy is coming from total potential. So total potential energy will be equal to half times by 2 times by 2 squared plus half times by 1 times by 4 squared. So 0.5 times by 8 plus 0.5 times by 16, 12 d. Okay, all right. A square board of side length x hangs freely from a nail PS. The board has uniform thickness and is made from material of uniform density. That means the center of gravity will be at the exact geometrical center. So if we can find the lengths of these and halve them, we can find out the difference between them, right? So the angles are 90 and 90, so they can obey the Pythagorean theorem. So this length is going to be half of, you can say, x squared plus x squared, and this length over here, this height, is going to be half of 4x squared plus 4x squared. Okay, so let's see. So 2x squared, so x times by under root 2 over 2, right? And this one, 4 plus 4, 8, and square root of 8 is 2 root 2, so just root 2x, because divide by 2 gets cancelled. So 2 root 2 divided by 2, 2 gets cancelled. Now the difference in the height is just going to be this minus this. Okay, the vertical distance is between that. So under root 2 minus half of under root 2. So that's just under root 2 by 2, or 1 over under root 2 basically. So that's B. All right. Okay, all right, moving on. Forces are applied to a rigid object. The forces all act in the same plane, in which diagram is the object in equilibrium. We know the two conditions for equilibrium. Two conditions for equilibrium are resultant force in any direction is 0, and the resultant moment is in any direction, if about any point is 0. So if we notice, let's see, all we have to do is sum the forces both upwards, downwards, and see if there's any moment about any point. So if we look at this, half f, resultant forces are equal to 0. F both upwards or downwards, resultant forces are equal. Resultant force is 0. Resultant force is not equal to 0, and half f resultant force is equal. Okay, all right. That means we have eliminated one possibility from the resultant force. Now let's look at the moment. Now for the moment, we know that the total moment should be 0 about any point. That's why, for example, if I choose this point over here, or let's say this point over here, the moment about both of these points, any point along the way, or any point over here should be 0. So assuming that this is like half this length over here, half x, let's say, for example. So over here, what we will have is f times by half of x, and then the other way minus plus, because clockwise is taken as negative, anti-clockwise is taken as positive. So half of f times by x. So this indeed is turning out to be moment equal to 0. Even if we take the moments about this point, that would also be the case. Now let's say for this second one. If we take moments about this one, then we have these two forces will cancel out because their moments will be equal, but this will cause a moment about this point. Same thing if we take a moment about this point. So this means that in the moments case, this is not correct. This will obviously not correct because you see the fourth, you will have some moment, non-zero moment. And for this one, let's say we take a moment about this point, you will have a non-zero moment over here. So right, so that means we only are left with A. Okay, a rigid body xy has a negligible mass and a length of 75 centimeter. A rod is suspended from a fixed point P by a string attached to the index. An object of mass 11 kgs is suspended from a string that is attached to the rod at a distance of 25 centimeter from end X. Okay, which vertically upward force acting on end Y of the rod would hold the rod horizontally in equilibrium? Okay, so basically we need an upward force over here. Okay, so this is causing a downward force, so that means clockwise moment. This is going to cause an anti-clockwise. So for horizontally, we need the sum of moments to be equal to 0, or clockwise, sum of clockwise moments equal to sum of counterclockwise or anti-clockwise moments. So we have over here, since both distances are in centimeters, so we can let go of that. So 11g times by 25 equals to 75 times by, let's say, f. Okay, so f would be 11g times by 25 divided by 75. So 11 times by 9.81 times by 25 divided by 75. So this comes out to be 35.97. So this. Okay, the density of the water is 1 gram per centimeter. The density of the glycerine is 1.3 gram per centimeter cube. Centimeter cube. Water is added to the measuring cylinder of 40 centimeter cube of glycerin, so that the density of the mixture is 1.1 gram per centimeter cube. Okay. Assuming that the mixing process did not change the total volume of the liquid. So basically what this means that there is no chemical reaction happening over here. Okay, so what is the volume of the water added? So total mass, so total mass is, we need to calculate what the total mass is. The total mass of volume would come out to be from, so 1 gram times by a volume of water plus 1.3 grams of volume of glycerin that they have given us 40 centimeters. Right, okay. So total mass, okay, right, okay, what do we know? So water is added to the measuring cylinder containing 40 centimeters, so that the density of the mixture, okay. Now when we divide by the total volume, now the total volume should be equal to volume of water plus this, this 40. When we divide by this, on the other side also, this should be uh, equal to 1.1 grams per centimeter. Okay, so now let's solve this equation because we just have one unknown here. So this becomes volume of water plus 1.3 times by 40, 52, equals to 1.1 times by volume of water equals to 1.1 times by 44. Sorry. So we take one thing on one side, so 1.1 V water, volume of water, 52 minus 44. So that means we have 0.1 VW equals to 52 minus 44, that's 8. So 8 divided by 0.1, that is 80. 80. Okay, all right, moving on. 15. A box in the shape of a cube falls from a ship into the sea. The box lands with its lower face level with the surface of the sea. The box begins to sink and becomes totally submerged and then sinks deeper into the sea. As the box sinks, the lower face is always parallel to the surface of the sea. Which graph best represents the variation of upthrust acting on the box with its depth of its lower face below the surface of the sea? Now, when we start off from the box starting at the surface of the sea, there's almost zero upthrust. When it starts to go a little bit deeper, the upthrust starts to increase due to the volume displaced increasing. Okay, so upthrust will start increasing linearly as the surface, as it becomes completely submerged in water. After that point, the upthrust will stay constant. Now, the only now point is this is down, this is gone, this is gone. These two might be correct, but which one of them should be the correct answer? Is the upthrust increasing linearly or upthrust is increasing uh, with a different curve, with a curve? So we know that the upthrust is equal to rho g a h, or depth in this case. The cross-sectional area remains the same. It's the depth that's changing. So we can see this over here. Upthrust is directly proportional to h. That means it will increase linearly. So C. Okay, a spring is compressed by a mass as shown. Which statement describes the changes to the energy of a spring when it is compressed by the mass? The spring gains both gravitational potential energy and elastic potential energy. The spring gains gravitational potential energy and loses elastic potential energy. It gains elastic potential energy. We know that. It doesn't lose elastic potential energy. And since it is a spring, it's decreasing in length vertically, so it loses a little bit of gravitational potential energy also. And it's gaining the elastic potential energy. So the reason it's gaining elastic potential energy is due to the loss of gravitational potential energy. So D. Okay, right. A man of mass, 75 kg, runs up a staircase consisting of 30 steps. Each step is 20 centimeters high. The man takes time 7 seconds to run from the bottom of the staircase to the top. What is the average rate of increase of gravitational potential energy of the man? Okay, so right, okay. So we basically need to see what is the total change in gravitational potential energy divided by the time. So m g, now h is 20 centimeters high, so that means 0.2 times by 30 divided by 7. So 75 times by 9.81 times by 0.2 times by 30 divided by 7. That is 630, so it's almost 630 volt. An alpha particle has 2.2 times 10 raised to the power minus 13 joules of kinetic energy. What is the speed of the alpha particle? Okay, so alpha particle, right, okay. So we have EK half mv squared equals to 2.2 10 raised to power minus 13. So we need the speed, right? So obviously we need to know what the mass is. So mass of an alpha particle in terms of uh, atomic mass unit, that's almost approximately 40 cube. So 2.2 10 raised to power minus 13 divided by, times by 2 divided by the total mass, which is 4 times by the atomic mass unit. We can go back into the data sheet and just quickly see, so you can also know where to locate that. 1 atomic mass unit, 1.66, 10 raised to power minus 27. Okay, so now let's see. 2.2 10 raised to power minus 13 times by 2 divided by 4 divided by 1.66 times by 10 raised to power 27. So 6, no, wait, sorry. This is the square. Now we will do the square root. And this is coming out to be 8.1 10 raised to power 6. Identical springs are joined in 4 arrangements. Which arrangement has the same spring constant as a single spring? Okay. So for this one, the total spring constant is divided by half. For this case, it is times by 2. Then k by 2, when they are joined in parallel, they will combine to make k, basically. And for this one, we have in parallel 2k in series with k. So 1 over k plus 1 over 2k. And that's not going to come out to be as a single k. So C is correct. An unstretched spring has a length of 2 centimeters. Okay, the spring is then stretched within its limit of proportionality by a tensile force of 1.5 newtons, so that the elastic potential energy stored in the spring is 0.05 joules. What is the stretched length of the spring? So elastic potential energy, we know that that is equal to half times by Fx. Okay, so extension. So elastic potential energy stored is 0.045, half times by tensile force 1.5, and extension is going to be L minus L naught, which is the extension. So we already know L, okay, Fx, that is L minus 2, and since these are in centimeters, we will need to convert it both of them into meters. Okay, now 1.5. Oh, wait, sorry. No. So let's find out what L minus 2 is. So 2 times by 0.045 divided by 1.5 times by 100. Sorry, times by 100. 2 times by 0.05 divided by 1.5 times by 100, that is 6. And then 6 plus 2, that is 8. 8 centimeters. Okay. A signal generator, amplifier, and a loudspeaker are used to produce different sound waves in the air of a room. The relationships between properties of these waves are investigated. Which relationship is not correct? Look backwards. Period is the equal to the reciprocal of frequency. This is correct. Intensity is proportional to the amplitude squared at a given frequency. That is also correct. Frequency is inversely proportional to wavelength. That is correct. Amplitude is proportional to wavelength. That is not correct. That's A. When a guitar string is plucked, it causes longitudinal sound wave in the air as shown. The speed of the sound in the air is 340 meters per second. What is the approximate frequency of the sound? Sure. So basically, to find out the frequency, we need the wavelength. So wavelength is basically from one compression to compression, basically. So basically, we can isolate this to be approximate, right? So this is to be the compression over here and this compression over here. So although this is slightly over here, we can say that this is, wait, this was 0.0, right? 2, 4, and 5. So roughly about 0.5 meters wavelength. So we have 340 meters per second divided by 0.5. 680, so roughly that. Okay, all right. A transverse wave travels along a rope. The diagram shows the rope at time t is equal to 0. The wave is traveling from left to right. The period of the wave is t, the direction of the travel. Okay. One particle of the rope is labeled x. Which graph shows the variation with time t of the displacement of particle x between t is equal to 0 to is equal to t? Wait, hold on. Transverse wave. Wave is traveling from left to right. The period of the wave is t. Okay, so if you notice over here, it's starting from 0, but now we need to figure out where it's going, whether it's going up or whether it's going down. Okay. So if it is going this way, so this curve will be coming right over here, like this, and then go like this again. Okay, so it's going downwards. It's still going down. So it's going to be at B. Okay. A jet aircraft travels at a speed of 0.80 v, where v is the speed of sound. Aircraft directly approaches a stationary observer. The frequency of the sound emitted by the aircraft is 100 hertz. What frequency does the observer hear? Okay, so we have frequency observed is equal to v minus vs frequency. This is the velocity or speed of sound, that is, let's say v minus 0.80 v times by 100 hertz. So this is basically v divided by 0.2 v cancelled. So 100 divided by 0.2, that is 500. A telescope detects and analyzes some electromagnetic radiation of wavelength 2 centimeters. Right, okay. Which type of telescope is it? So wavelengths 2 centimeter basically means around 10 raised by minus 2 meter scale over here. So that is in the microwave region. Radio is in meters basically. So that's going to be micro. X-ray obviously is not going to be 2 centimeter. Optical also not. Two waves from the same type, two waves of the same type overlap. When does the principle of superposition apply? So always only when the waves have same amplitude, same frequency, travel in opposite directions. So that's always going to apply. Okay. Same amplitude we need when we need a steady interference pattern. Steady or at least observable interference pattern. Same frequency, we don't actually have that problem. And actually that's for the same reason. Opposite directions, that's one of the conditions for stationary waves. stationary waves, and also for the same frequency. Okay, a stationary sound wave is formed in a tube of the L that is closed at one end. The diagram shows the position of the nodes and antinodes of the stationary wave. Which graph shows the variation of amplitude A of the wave with distance x measured from the closed end of the tube? Okay, we're talking about the amplitude. Amplitude is just the maximum displacement, not the displacement. So if we look at this, node is where it's zero, antinode it's where it's highest. Oh no, sorry, no. It's the other way around, like this. So amplitude is just the highest at the antinode, then node over here, antinode over here. So yeah, amplitude doesn't go to zero because that's in, what we say the maximum displacement. It's not the displacement. Okay, all right. A wave on the surface of the water passes through a gap between two barriers and is diffracted as shown. What happens when the frequency of the wave is halved? So when the frequency of the wave is halved, the wavelength is doubled, right? So when the wavelength is doubled, we will observe more diffraction than this. That means there will be more bending of light. Okay. Observable interference fringes are produced using light from a double slit. The intensity of the light emerging from each slit is initially the same. The intensity of light emerging from one of the slits is now reduced. How does this affect the interference pattern? So basically what this means is that when we say intensity of one of the slits is now reduced, we are actually reducing the amplitude. Okay, so one of the amplitude is reduced. So for example, when one wave is this, the other wave is sort of like this. Although this is for one of the waves. So obviously this will affect the superposition in total. Okay, so the bright fringes will become less bright and the dark fringes will become less dark. So bright fringes and dark fringes all become brighter? No. Bright fringes and dark fringes all become darker? No. The bright fringes become brighter, dark fringes become darker? No. Bright fringes becomes darker and dark fringes becomes brighter. That's the case. The contrast basically that's affected. The diffraction grating has 4 to 10 raised to power 5 lines per meter. A beam of light of wavelength 589 10 raised to power minus 9 meters is incident normally on the diffraction grating. What is the angle between the second order maximum and the direction of the incident beam of light? So basically we need to figure out, this is the n is equal to 2, we need to find out this angle over here. So n lambda is equal to d sine theta. So we need to find out the sine theta first. N lambda divided by d, so 2 times by lambda, 589, 10 raised to power minus 9, divided by d, which is, oh, this is the lines per meter. We need the line spacing. So 1 divided by that would be the answer. So 1 divided by, so 1 divided by 4 10 raised to power 5. So that's this value. Well, I'll just keep that as it is. 2.5 10 raised to power minus 6. Now let's put this all under in sine inverse. So 2 times by 589 divided by 3.5 times 10 raised to power minus 9 plus 6, that is just simply minus 3. So that's 28.1. Okay, all right. A length of wire RS has a circular cross section and End R of the wire, the cross-sectional area is A, at end S of the wire, the cross-sectional area is A by 2. Charge Q takes time t to pass through the end R of the wire. There's a constant electric current in the wire. Oh, okay. How much charge will pass through end S in a time interval of t by 4? Okay, so we know that I is directly proportional to cross-sectional area, and also the charge basically, A and Q, right? So if we write the full form, that is equal to this. And we also know that this is equal to total charge over total time. Okay. So if the current is the same, that means either the drift speed is allowing for the balance to between the charge and the current passing it's been maintained. Okay, so that's what we have to figure out. However, it still means that the rate of charge over time passing is the same. So the time it takes for, let's say for example over here, t by 4, that would be q by 4. And if the current is the same, that means rate of charge flow is the same. So in t by 4 time, we will have charge q by 4 also. A power supply is connected to a component by connecting wires of total resistance 4.9 ohms. Okay, to a component by connecting wires of total resistance 4.9 ohm. The power supply has an output power of 3.6 watt and a terminal potential difference of 12 volts. How much thermal energy is dissipated in the connecting wires in a time of 1 hour? Okay, power is equal to VI, so you can use this output power to determine how much current is flowing. So if the terminal potential difference is 12 and power supply is 3.6, so 12I, I will be equal to 3.6 divided by 12, that is 0.9. So energy will be equal to IVT, I squared RT, 0.3 times by 4.9 squared times by 3600 for 1 hour. So 0.3 times by 4.9 times by 4.9 times by 3600. That is sorry, my bad. I squared the wrong term. 0.3 squared. Okay, that is 1587. So roughly this. Sorry, my bad. This was I squared. Okay, copper wire is to be replaced by an aluminum alloy wire of the same length and resistance. Copper has half the resistivity of the alloy. What is the ratio of the diameter of the alloy wire and diameter of the copper wire? Okay, so copper resistivity is 1/2 of that copper of the alloy, right? So resistance is the same, L over A, and basically that's pi d squared over 4. Okay, so this means that if resistance is the same, length is the same, the only things that are changing is resistivity and the area. So basically you can say that area is directly proportional to resistivity, or in short, resistivity is directly proportional to d squared. Okay, so this same relationship will be extended to d squared. Okay, so if I have rho c, we need alloy, that will be diameter of alloy, diameter of copper. So if this rho c over rho a was 1 over 2, so diameter of alloy and diameter of copper will share the same relationship. That will be, sorry, it's the other way around. That's 2. because you see that's copper. Sorry, my bad. Copper, right? So that means when we take the square root, diameter A, diameter copper, that will be square root of 2. That's this. Okay, all right. 34. Three identical filament lamps, P, Q, and R, are connected to a battery of negligible internal resistance as shown. The filament wire in lamp Q breaks so that it no longer conducts. What are the changes in the brightness of the lamps P and R? So if the Q is not working anymore, the total effective resistance of the circuit increases. Okay, so because the resistors in parallel only reduce the effective resistance. So when this is gone, the total effective resistance will increase slightly. Okay, so uh, right. So since the current is going to increase, resistance across even this combination is increasing, so the lamp uh, will be brighter. Lamp P will be brighter. And since the potential difference across this combination has increased, the potential difference across R would simultaneously be decreased. So dim. Which ratio has the same unit as the electromotive force? So V is basically energy over charge. So joules per coulomb, basically. So charge per unit, no, energy transferred per unit charge. That. Okay. A circuit consists of a battery, voltmeter, and 5 fixed resistors as shown. Voltmeter reading is 0. What is the resistance of resistor R? Okay, so if the potential difference across this is 0, that means that the potential difference across across this is equal to potential difference across this, or vice versa. Potential difference across this is equal to the potential difference across this combination. Okay, so this is what we need to figure this out first. So the potential difference, the so potential difference across this 5, 10, and 2, 8 is going to be equal or equivalent, right? So what we're going to do, we need to figure out what ratio it is. So that's 5 ratio 10 basically, right? So 5 ratio 10 for the potential difference over here. So 5 over 15 uh, of V, well, let's call that V. And this is going to be 10 over 15 of V. Similarly, this has to be the same thing. So this has to be the same 5 over 15 V, and this has to be the same 10 15 of V, so that the potential difference across this is 0. Okay, so if we can figure out the resistance ratio over here, we can figure out that. So basically the ratio is the same, 5:10. Ratio is 5:10, or basically 1 ratio 2. So now coming on to this, 2 ratio 1 over 8 plus 1 over r, uh, for this combination, that will be equal to 8 plus r divided by 8r, right? So r effective, 1 over r effective. So r effective will be 8r over 8 plus r. Okay, so now we can calculate that by simply cross multiplying. So 8r over 8 plus r is equal to 4. So 8r is equal to 4 times by 8 is 34. 32, sorry, my bad. Plus 4r. And then 4r equals to 32. So that's 8. R is 8. Right. Okay. Uh, a battery of electromotive force EMF 6 volts and negligible internal resistance is connected to a voltmeter and four other components as shown. The voltmeter is connected between points X and Y. The positive terminal of the voltmeter is connected to X and the negative terminal of the voltmeter is connected to Y. Initially, the resistance of each of the four components is 1 kilo. What change on its own will cause the voltmeter to show a positive reading? So basically, this means that the potential difference across this rises and the potential difference across this is decreased as comparison, right? So if we think about this, either, so this is a variable resistor, right? So if we need to increase the potential difference across S, we need to decrease the resistance of variable resistor. Okay. Similarly, if we need to decrease the potential difference across this, we need to decrease the resistance or increase temperature. And likewise, we can, since we want the potential difference across this to increase, right? So this is a LDR basically. So potential difference increase means resistance increase. So the light intensity has to increase. Okay, so let's see which one of them. So decrease the temperature, no. Increase the resistance, no. Reduce the intensity of the light incident on, yes, that is correct. Okay, all right. 38. A alpha particle close to a gold nucleus passes close to a gold nucleus and is deflected through an angle greater than 90 degrees. Which property of the alpha particle changes as a result of deflection? So it's basically just the momentum. That's all. Charge is not altered, nucleon number, proton number is not altered. It's just the deflection is just causing the change in momentum. A nucleus of uranium decays in stages by alpha particles and beta negative particles, eventually forming a nucleus of lead. Right. How many alpha particles and how many beta negative particles are emitted during the decay chain? Okay. So first off, we need to think about the decrease in the nucleon number, because in beta decay the nucleon number doesn't change, so we have to go up till the nucleon number change at least. So alpha particles will be equal to 238 minus 206 divided by 4, because nucleon number reduces by 4 each time, minus 206 divided by 4, that is 8. Okay, but what that does to the proton number also decreases by 2. So if the proton number decreases by 92 minus 8 times by 2. So 92 minus 16, 76. So we need to increase the proton number by 4, which means that we need 4 beta particles, because we know that in beta negative particles, proton number increases by 1. So 76 plus 4 times by 1. So alpha particles 8. Sorry. No. Sorry. 6, my bad. 6. 8 and 6. 82, my bad. 6. Which list of particles contains only fundamental particles? Antineutrino, beta, meson. Meson is a hadron, not a fundamental particle. Baryon, neutrino, no. Electron, neutrino, alpha, no. Lepton, quark, positron, that's correct. That's our answer. All right, and that's the 40th question, and that's the end of the paper. All right, so see you in the next paper. Bye-bye.